Hello guys, welcome to the new installation of this class, and please turn on your cameras if you are present. Good. I'm grading your exam. I flagged the people that cheated. There would be a segment there saying copied. Okay, I'm not sure if I will take immediate actions about it, but make sure, guys, that when you write something, write your own work. It's especially obvious when you copy something that is rather made in a very poor way. I will bring you the exam. I think by the end of this week, I probably will give you the exams back. Okay, somewhere on the weekend. And the new exam is just around the corner. So we talk about Poisson random variables. That's where we were last time. So do you remember this formula, guys? Yes, so a Poisson is a random variable that uses the exponential e, and it's of parameter lambda if the probability that x equals to k is equal to e to the minus lambda, lambda to the k over k factorial. Now, we mentioned why such a distribution becomes important. Now, for example, it's a very good approximation to the binomial theorem under several assumptions. Now, would you remind me, anybody, what are those assumptions? Very roughly, what's the assumption that makes the Poisson a good approximation? Okay, very good, very large n. That means lots of trials. And what else? And p is very small, so small that the product of n multiplied by p will be a number considerably smaller than n, considerably smaller. So especially when you have comparisons, they don't have to be that extreme, but if n is around millions of trials, and the n multiplied by p, that's the expected value, that's the expected number of successes on binomial trials, right? That might be like 5 or 7, or right? Something that is extremely small compared to the number of trials. That means we have very little chance of success, but we have lots of trials, so that the average is very, very far removed from the maximum value that n can reach. And this is the derivation. I hope you actually carried it. Good. So lambda then represents the product n multiplied by p. Lambda, this parameter, is the expected value of the binomial. Yes. Now it's very, very useful also when you do not know the actual probability of success and you do not know the actual number of trials. Right, all you need to know is the product, and we saw several examples of that. So, for instance, the number of errors on the page. So we imagine lots of letters, and we imagine each letter might be either correct or incorrect randomly. We can pretend it's binomial, and we might just find on average, just by scanning the document, that about one error per 2 pages, right? So that's what the 1/2 here means. N times p is 1/2, means about 1 error per 2 pages, or 1/2 of an error on average per page. It means one letter is out of place, out of many, many trials of letters. And then we can use the Poisson to estimate the probability that there will be more than one error or more than 0 errors on a particular page. And especially this is very well working when you have radioactive material. So you have alpha particle emission, and that is just the average. If it's say on average in 1 second, some radioactive material releases 3.2 alpha particles, that means that we have billions upon billions of atoms, and each is very unlikely to release an alpha particle, right? So the success is very low, but the average success is the 3.2. On average, that's how many we have. Good. And we can see that then we have a very good approximation by the Poisson. So it ends up also working for distributions that are not binomial, but where the dependence is weak enough. Okay, so we are not going to go through the precise conditions. They are very difficult. The precise estimates of when Poisson works and how to do that, that's another story. But you can have a sense in this class of when it is a good approximation, right? All right, so we did this example here as well. That's where we had n distinguishable boxes and can distinguishable balls, and we placed each ball is equally likely to be in any of the boxes, and then we calculated the approximation to the probability that at least one box is empty, right? So if we have, let's say, 1,000 boxes and 5,806 balls, we decided we could figure out what's an approximation that at least one box is empty. So then what you can see is we can calculate the expected number of empty boxes, right? The expected number of empty boxes is given here. It's just we can say it's just whether or not x1 will add 1 if box number 1 is empty, and x2 will do that for box number 2, and so on and so forth, right? So then we can calculate the expected value of x1 all the way through xn, and we know that they are going to have the same distributions. So the expected value of any xj, for instance, it means that all the balls went to other locations. It's 1 multiplied by the probability that no ball enters the j box. And that probability is n minus 1 over n for each ball to the power of k, right? And this n here appears because we have additivity of the expected value. So it's expected value of x1 plus expected value x2 and so on. Good. And then, of course, this allows us to, because we know the expected, we know this expected number, right? We know we can calculate it. Here is the general formula. We know that the expected value, if you have 1,000 boxes and 5,806 balls, this is the expected value, right? And we can simplify this expected value slightly. So this is going to be my lambda, right? That's kind of like the probability multiplied by the trial. It doesn't have to be, as I mentioned, binomial. It has to be somewhat weakly dependent, right? So clearly, this is not a binomial formula, because if box 1 is empty, that will influence the probability of whether or not box 2 is empty. Yeah, so it's not binomial, but if we have many boxes, just for instance, if you compare any two of them, just compare box 1 and box 2, what happens in box 1 is going to be very weakly influencing what happens to box 2, usually, right? So what you have here is that the expected value is this number. With this number, we can approximate to be approximately 1,000 times e to the minus 5.806, and this number is approximately 3. So this expected value, this we can just simplify and see that this is approximately 3, and we so use Poisson with parameter 3. And so the probability that more than one box is empty is the same as 1 minus probability that that no boxes are empty. And that's simply approximately 1 minus the probability for the Poisson, right? So this is the Poisson. So it's 1 minus e to the minus 3, and it's 95%. Yes, and then that can be used to approximate a lot of difficult probabilities, including the birthday problem. Yes, guys, I hope I'm not going too fast. If I am, you let me know, right? I mean, I did cover that last class, but I'm not sure if you were all able to follow it. Were you? Or not? Yes. All right. over the Poisson, guys. So let me know if there is something you want me to go over, but do that quickly. Don't be staring into the headlights, please. What would you like me to re-explain, if anything? So the most important part here is just that the Poisson is a good approximation to the binomial and to see this derivation, right? Anybody needs to, you want me to go over the derivation again, or you more or less have the sense of how to do it yourself? Right, so make sure, guys, that when you end this lecture or sometime when you just can find this moment for yourself, verify why the Poisson is working, because so otherwise, what am I really useful for? Would you like me to go over that again, or you understood the derivation? Please write N or Y, or just show me that you're breathing. Okay, one person says yes, please. Yes, okay. Okay, good. One more time. Let's try. So again, guys, we are assuming we have a binomial distribution where with some n, and we want to know the probability that x equals to k. And that would be n choose k, p to the k, 1 minus p, n minus k. So far, clear, correct? It's just binomial, you are with me. Yes, good. Next, what do? We simplify it a little. So we can write n choose k as n factorial divided by k factorial, n minus k factorial. No trouble there. Next, I see a p, right? Where I see a p, I want to see the expected value. I want to see n multiplied by p. So the assumptions of Poisson is that I believe there is a p, I believe there is an n, but I not necessarily know them, you understand? So so I know n multiplied by p, but not n by itself or p by itself necessarily, right? And that maybe because of some experiment. Like, again, think of the radioactive decay. That's the best way to think of it, right? Radioactive decay, just imagine each atom is a trial, and independently of another atom, it releases an alpha particle or does not release an alpha particle. And I'm not actually going to, I cannot right away, I just don't have this one atom, and I do not measure the probability that it will release an alpha particle, right? I just believe there is a probability p. It's small, right? And because you have so many trials, you imagine each atom is identical to another. So you have billions upon billions of trials. So when you do the experiment and you measure how many alpha particles are emitted, you actually see the average. You see n multiplied by p. If you understood how the average works, right? It just n multiplied by p is the number of successes. Right, it's going to be very regular. In 1 second, this gram is going to release essentially 3.2 alpha particles, if that was your observation. And the reason is because you remember, it's like with the will, it's the expected value. It's like you have many trials, right? So that's the expected value there. So yes. Makes sense, yes, guys. You understand how the so what you do is you record one time, another time you record the alpha particle released, and then you know the average pretty much from there. So then what do? So then instead of writing p, you want to have np. So what do? Just multiply by n and divide by n, because you cannot just multiply without simplifying. Yes, and you see at p over here, you do the same. Good. So what do you have here? Now this is your lambda. This is lambda over n, and this is lambda over n. So what do you get? You get here, and I break it apart a little bit, right? So what is this? This is lambda to the power of k divided by n to the power of k. And I separate the n to the k and I move it here. You see what I do? I take n factorial over n minus k factorial. First of all, I get rid of the n minus k factorial, and I just write it as n minus 1 all the way to n minus k plus 1. So the n minus k factorial was simplified. Next, from this is lambda, and this is n, right? So I have lambda to the k divided by n to the k, and I move the n to the k below this line. This is n to the k here, right? And what do we have here? This is simply 1 minus lambda over n to the power of n. Do you agree? Divided by 1 minus lambda over n to the power of k. And the k factorial, here it is. I just moved it. With me? Yes? Wonderful. And what next? Next, I look at this expression. What can I write here? I can write it as n divided by n. They are crossed out. N minus 1 divided by n, n minus 2 divided by n. For each of those, I have an n available. Do you agree? For this n, for this n, for this n. So I just distribute the n, and I have those expressions. Now, what happens if n is very large, but k compared to n is small? I'm not going to be asking probability for large k's, because I mean they're going to be extremely small, right? So that's the assumption, at least, right? So the number of successes is going to be considerably smaller than the number of trials. If we have n trials, we have maybe millions of trials, but we have maybe 5 successes. That's a very small number compared to a million. So k, I'm not going to ask for maybe k beyond 20 or something, right? So k is a small number, and n is a very large number. So what do you see? You see that this ratio and this ratio and this ratio are almost all of them equal to 1, because subtract from a million, subtract 5, you barely notice it, right? Take a million minus 5 over a million, you get something very, very close to 1. Slightly smaller than 1, but very, very close to it. And that's true for all of those ratios. So this is almost 1, this is almost 1, this is almost 1. This is just lambda to the power of k. Is the expected value, right? And what about the denominator here? 1 minus lambda over n to the power of k. This here, k is small, so it's like 1 minus, essentially almost minus 0 to the power of k. So it's like 1 multiplied by itself several times. So it vanishes, you see? When I rearrange those terms and under proper assumptions, they vanish. What doesn't? So this vanishes, this vanishes, this vanishes. All of them vanish to 1, to be precise, right? All of them become 1. What is left? This is left, and this is left, and this is left. Yes, 1 over k factorial. Now, what is the numerator here? What is this? N is large again, and lambda compared to n is not very significant. So this looks like e to the minus lambda. Do you agree? If you remember that limit, we derived it when we did a review before beginning chapter 2 for probability. We did a review of this limit. So this limit you recognize as e to the minus lambda. Yes, it's e to the minus lambda. This is lambda to the k over k factorial. And what do you get? You get precisely this formula. You get precisely the Poisson distribution, right? So when you kind of play around with it, you can, by deriving it, you remind yourself of the property that this distribution has. Good. And here again, this question, you understood it. So you open to page 100 in the book. What's the probability you find a typographical error? You averaged a bunch of, you have this average information. So based on that average, you can estimate what's the probability of having an error or more than one error, because you know that you can imagine that this letter is either correct or not, the next is either correct or not. So you can imagine that each letter is like a trial, and it has very low probability of being the wrong letter, right? You can, in your mind, at least simplify it for a moment and say, well, imagine that each letter is going to be the right letter with probability 0.99999, and the wrong letter may be any one of other available letters with some other probability, right? And then you see that on average for each trial you have there is a small probability of finding a mistake. It's going to be, the average is going to be 1/2. So that can be your Poisson parameter lambda. It's 1/2. Yes, and then you see that the approximate probability is that you find one or more errors is 1 minus e to the minus 1/2, because it's 1 minus the probability that the Poisson is equal to 0, right? And then you have this approximation. Again, I mean, you can investigate the Poisson much more deeply and actually ask. It's important to ask how bad is the error, how bad is this approximation, how close it is to the real thing, right? We see by the limit that, I mean, provided the numbers match good enough, then we can approximate the binomial theorem. But when in practice is it a good approximation? When not, that's a much more difficult question. For this class, you have to just have to sense it. You don't have to be too precise. Yes. And this is the alpha particle question. Again, I hope you understood it, right? The alpha particle, again, I know the average. I know that in 1 second on average, I get 3.2 alpha particles because I did the experiment. I didn't actually measure the probability, I just did the experiment. And then I averaged the results and I see that 3.2 is the average, right? And from there, I know what's the probability that I will have 2 or less alpha particles in the next second. Why? Because I can approximate this with Poisson. The average is n number of atoms or number of trials multiplied by the probability that it releases an alpha particle. It's n times p. It's equal to 3.2. Yes, and that's what we get. We get the probability that it's equal to probability x equal to 0 plus x equal to 1 plus x equal to 2, and that's approximately this, right? It's e to the minus 3.2. because that we have divided by 0 factorial. Then we have e to the minus 3.2, 3.2 to the power of 1 divided by 1 factorial. And the same thing with 3.2 squared over 2. That's that's for the Poisson being equal to 2. And you add those things up and you get an approximation of about 40%, of about 38%. Yeah. And here is another example. That's, by the way, another question on the exam that almost nobody got correct. And that was the question about the breath. What's the probability that you breathe a molecule of that came out of as the last breath from Julius Caesar? Yes. Yes, that makes sense, guys. So this question, most of you somehow missed. It relates to, again, I mean, the reason you would actually see an E in such questions is because of Poisson distribution. Each trial is success or failure. You have many trials. Each individual success is unlikely. Yeah. So yes. So then just let's review this question about a website here. So imagine that a website is visited by 1 million people a day, could potentially come to this website. And each person is very unlikely to visit this website this particular day, right? It's just 2 times 10 to the minus 6. So it's not a very tremendously popular website. So how many visits are we going to have? Right, so or what's the probability that we have at least 3 visits? That's the question. So directly you can see that that success is very unlikely for each individual, but we can calculate the average success. See, you can do it by the binomial, but you get very ugly big numbers. But you can instead reason as follows. So I know what's going to be the average number of visits because I take this number, the probability, and multiply by the number of trials, by 1 million. So it's 2 times 10 to the minus 6 times 10 to the 6. So it is 2. On average, I get 2 visitors. You see, I have 1 million possible visitors, but I only get on average 2. So you can see much smaller than the number of trials. So probability is small, right? So on average, I get 2. So that makes lambda equal to 2. That's a good approximation there, right? So probability that x is less than or equal to 3 is approximately the probability that the Poisson with parameter 2 is less than or equal to 3. And that is the same as 1 minus probability at 0 minus probability at 1 minus probability at 2, which is 1 minus e to the minus 2, 1 plus 2 plus 2 squared over 2. This formula makes sense, yes? Good. You see how I calculated this, correct? Thank you. Oh, good, right? So that now I estimate to be 32%, and that's going to be incredibly accurate. Incredibly, it's very, very close to the actual binomial probability. Yes, that has to do with, of course, convergence. How quickly are those estimates converging? Yes, and you can see that the lambda is much smaller than 10 to the 6, and 3, the number of successes I request, is much smaller than all of them. So Poisson is a natural way to go. And then again, when the outcomes are not independent, they're not independent trials, it's not as easy to see that Poisson is a good choice, but it's very, very frequently ends up also a good approximation. So the fact that 2 outcomes are weakly dependent is not going to terribly affect the Poisson. It can still be used as a good estimate. And here is the birthday problem that we solved before. So here we have n people in a room, and we want to estimate what's the number of n people, what's the number n should equal to, if I want at least a 50% likelihood that 2 people match on a birthday. Yes. And what is that? So, well, if I have n people, I can imagine the problem of matching is it has n choose 2 trials. You agree? Because we compare at a time every possible 2 people, right? So so that's why it's n choose 2 trials. Make sense? So it's not just the number n. If, for instance, you have 4 people, how many comparisons will you try to achieve? You would have, if you have 4 people, it would be 6 comparisons. You agree? Because you have first person and second, first and third, first and fourth. And then we have a second person with third and second with fourth. And then we have third with fourth. So we have lots of trials. They are not independent. We have many more trials, especially if the number gets larger, then n choose 2 is growing much faster than n is growing. Right? It's growing with more or less the square of n. So that's how many trials we have. The expected value is not affected by dependence or not, it's additive, right? So we can just take a pair of people. The probability they match on a birthday is 1 out of 365. And the reason for that is that they each can have a birthday on any of 365 days. That makes a total birthday combination 365 squared possibilities. And for them to match on the same day, they can match on any of the 365 days. So it's 1 out of 365, right? And then the expected value for all of them on how many matches you have is n choose 2 times 1 over 365. Make sense? That's because it's additive. So just the expected value of for person 1 and person 2 to match is the same for any other. Good. So then we get this number. We get that my lambda parameter, my average that I plug into the Poisson is this number. And so when I want the probability, the estimate is the probability that I have 1 or more matches, where y is the approximation here, right? It's approximately Poisson here. So y bigger than or equal to 1 means y minus the probability that y is 0. 1 minus the probability y is 0 is bigger than or equal to 1/2. And that is, if you rearrange everything, it's just the same as 1/2 bigger than this number. Because that's probability y equals 0 is e to the minus lambda, right? And it has to be smaller than 1/2. And that's the same as I just apply logarithms, right? That's the same. You can just either do what I did here, or just take logarithm of this side and logarithm of that side. Logarithm is an increasing function, so it preserves the same relation, right? So logarithm of this number is going to be bigger than logarithm of this number. And that's the same thing as saying that that this number is bigger than ln of 2. Does it make sense? You remember logarithms enough for me not to need to explain this, or am I wrong? You'll see this calculation. Yes, guys, so this number is bigger than or equal to ln 2. And then from there on, it's just a quadratic equation. Just rearrange it into a quadratic equation, and you see that for this calculation to be true, n has to be bigger than this number, when n is an integer. So this number is closest to the integer 23. So n has to be, look at this number and take the ceiling. So whatever number you get maybe 22 point something. Just take the ceiling and you see it's 23 that you need to have. Yes? So that's 23. Yes, bigger than, no, so bigger than here than ln of 2. So if you take logarithm of 1/2, is going to be bigger than minus this number.
Professor, I mean, I didn't understand Poisson of more than one people, bigger than a half. What is it, a 1/2 means?
Because we asked for 50%.
Oh,
so we want the probability that we have a match of one or more to be more than the probability 1/2. So this is the probability that I have a match, one match at least, to be bigger than 1/2.
All right.
Right. So it makes sense why they placed the 1/2 here. It's only because arbitrarily it was decided that we want the probability to be bigger than 1/2. If I wanted to be bigger than, let's say, 9/10, then I would place 9/10 there, right? If I wanted it to be bigger than 90%, right? It's going to be a different number. You can carry that calculation as well. Right? So then I rearrange things and I solve, and I get n bigger than or equal to 23. You see, and that ends up being a very, very good approximation. You could have done it from scratch. I mean, you could have figured it from scratch if you tried. Just you have to recognize that when you have something complicated, you recognize that you have the limit value of e appearing, or e to some power, and you use that. Okay, so for instance, so what should be the number of people in room n so that having the same or consecutive birthday probability is 1/2 or more? You see, so it's a slightly modified question. We are saying same, they have to have same birthday, or they can be different by 1 day, right? So clearly we should have fewer people for that. Yes. So then how do we do that? Just as before, we have n choose 2 trials, but this time we have many more possibilities, right? If we have n choose 2 trials, imagine when I do n choose 2 trials, the people are arranged in alphabetic order, a person that, alphabetic order. So just let's say if I compare myself with Camille, because my first name is A and his first name begins with K, I come to the left and he is placed on the right, right? That's how I report it. So what happens then? We have n choose 2 trials. Now, what could happen? It could be that that my birthday is the day, if we match the day before his, exactly on his day, on the day after, right? The day after his. So that's why I have the 3 here. Make sense? So it's 3 times 365. So let's say we can focus on a particular date. Let's say it's maybe January 1st or January, you understand, and rearrange. Make sense? So it's going to, the probability of success is now 3 times as high. It's 3/365. We just for every day, we just we have mine. It could be this day. His could be this day. For every 1 day, we have 3 possibilities. All right. So in this case, just if you work as before, you get that 3n times n minus 1 is bigger than or equal to 5 or 5 or 6. So just you do the same calculation as over here, but using this number. So your expected value is n choose 2 multiplied by this. And when you carry the same calculation, you end up with this line, and that will correspond to n being 14 or more. So you just need 14 people for the probability to be bigger than 1/2 that the people either match or differ in one day. Okay. Now let's talk about the expected value and variance of the Poisson random variable. Now, expected value should be obvious, right? I mean, the expected value should be the same as lambda, should be the same as the expected value for the binomial, which is lambda. That's by intuition. You agree? Because if the Poisson is simulating a binomial distribution, they should match as closely as possible in their expected value. We're going to verify it. Now, what about variance? Variance of the binomial is n times p times 1 minus p. Make sure that you know how to derive it. Okay. Now, if p is very small, then 1 minus p is very similar to 1. You agree? So variance is also the same as the expected value. You see, because it's just np. So we are expecting the Poisson to have both variance and expected value equal to lambda. And let's verify that this is indeed the case. So first, the expected value is, if you calculate directly, this is what it is defined. It's the probability multiplied by k, where k is the number of successes. Yes. Now, what can you do here? First of all, it's k. K could be 0, 1, 2, all the way to infinity. Then clearly, if I multiply by k, I don't need a 0. I can start it from 1. And if I start it from 1, I can have k divided by k factorial is just k minus 1 factorial. You see this? So you see the cancellations are pretty easy. And then what do I do here? All I need to do, look at it, this is the same summation. It's like 0 factorial, 1 factorial, just lambda is raised to a power by 1 higher than than k minus 1, right? So it's what? It's 0 factorial lambda to the 1 plus 1 factorial lambda to the 2. But I want lambda to be raised to the same power as what's inside of the factorial. So what do? I factor out a lambda, and then I see that it's the same exact. I just relabel it back to k, but it's exact. What the idea is that it's exactly the same summation. Yes. And what is this summation? This summation is e to the power of lambda. Do you recognize it? It's just the polynomial, the infinite polynomial, or the Taylor polynomial for e to the lambda. So it's e to the minus lambda, lambda, e to the lambda. When you simplify, you get lambda. Similarly, we can calculate the expected value of y squared, right? The expected value of y squared is, we have a k squared here. And what we can do, what we can do, again, we can start it from 1 because k is 0, it's, we don't need to consider that term. And then I can yeah, so what do I do next? Next, I factor a lambda, right? I factor a lambda, I kind of shortened a lot of calculations here. So I factor out a lambda, and I cancel one of the k's, you see? So maybe I will write it for you separately, since if I got stuck for a moment, that means that it might not be clear enough. So we are interested in the summation, yes? So k1 to infinity, k squared lambda to the k factorial, yes? Now, what can I do first? I can take the lambda and factor it out. And I can cross out one of the k's. Do you agree? So what do I get now? I get k. And here I have lambda to the k minus 1 divided by k minus 1 factorial. Agreed? Everybody sees what I did. I crossed out 1k, and yes, and I still have 1 in reserve, and I have this. Okay. Now, what is this? Now, if this, I can say, well, I can just relabel it back to, maybe I'll just use j so that it's not too confusing for you. So it's the same as lambda. Then I can write this as j equal to 0 to infinity. And here I have then lambda to the j divided by j factorial. Agreed? Yes. But if this is j, then this is j plus 1. You agree with me, guys? And then what? And then I can distribute it. I can distribute this expression. And what do I get? I get lambda summation j equals 0 to infinity of j lambda j over j factorial plus the summation j equals 0 to infinity of lambda to the j divided by j factorial. And what do I get here? Here, I clearly see that it's just e to the lambda, right? So this part is e to the lambda. Now, what is this part? This part looks like the expected value, right? This is the expected value, but what's missing is e to the minus lambda, right? So what I will do is, I call it wishful thinking. I place here an e to the minus lambda, and I divide by it, so it's e to the lambda, right? So this is then okay, so still kind of lost how factoring out a lambda leads to k squared being k. I again simplified 2 steps. So factoring a lambda, now you still have the k squared here, and here you have k factorial. Do you agree that in here I can cancel one of the k's? So I can place here a k minus 1 factorial, and by that I remove the square. Does it help? Yes, good. Makes sense, guys? So then what is this? This is e to the lambda, this part. And the first part of the parentheses, look at it, it's e to the minus lambda. I put an e to the minus lambda and I multiply by e to the lambda. Why? Because what I see here in this parenthesis is now the expected value of, so this is the expected value of the Poisson. Maybe I called it y, I don't remember. So it's the expected value of the Poisson plus e to the lambda, and the expected value of the Poisson multiplied by lambda, and all of it multiplied by lambda, right? I believe, right? So this is what this is just e to the lambda. This I decided to write as e to the minus lambda times this, so that's the expected value of the Poisson. And here is what I paid for it, right? I have to factor out e to the lambda then. So it's this, and then multiplied by lambda. Now, what do we know about the expected value? We already calculated it to be lambda. So this can be simplified as lambda e to the lambda, factor e to the lambda. And then here we have lambda plus 1. One second, something is. What? This is what this calculation is. It's lambda e to the lambda, lambda plus 1. Everybody is good? Now, remember that when we began calculating it, right? When we began calculating, the entire thing has to be multiplied by e to the minus lambda, right? So the entire thing, I'll put it in green. So we have to multiply this by e to the lambda. I just didn't include e to the minus lambda. That's the probability, right? Because when we calculate the expected value of y squared, it's the square, but times the probability. But the probability always involves e to the minus lambda. So when I multiply it by e to the minus lambda, I multiply it here by e to the minus lambda. And then what do you get? You simply get lambda plus 1, or if you prefer, you just get lambda squared plus lambda, right? I hope it makes better sense. Yes. So yeah, so when I say what is the variance, I get this expression. You see, that's the e to the minus lambda. I multiply it by the end of it. I just kind of for a second froze on this calculation. And that's why I showed it to you. Now e to the y squared minus e to the y squared is what? It's this number minus, we know what's e to the y, it's just lambda. So it's that minus y squared. So it just ends up being lambda as expected. Good. Now some properties of Poisson random variables. So if x is Poisson with parameter lambda 1 and y is Poisson with parameter lambda 2, and these variables are independent, then x plus y is also Poisson with parameter lambda equal to lambda 1 plus lambda 2. Okay. So we can combine Poissons. And now, why is that the case? We want to understand what is probability that x plus y equals to k. Right? You agree that x, if it's Poisson, it can equal 0, 1, 2, 3, 4, all the natural numbers, including 0, and y can do the same. Okay, and we assume the independence. So what's the probability that x plus y equals to k? Well, it is it means what? What's the ways for this to happen? X equal to 0, y equal to k, x equal to 1, y equal to k minus 1. Do you agree? In general, x equal to j, y equal to k minus j, right? So the probability here is identical to all the summation j equals 0 to k, probability x equal k, y equal, so x equal to j, y equal k minus j. And they're independent, so this product can be brought into one multiplied by the other. It's independence. Makes sense, guys? Yeah. So this is just conditioning. It's the probability that x is one value, y is another. Because they're independent, I can break it apart like this. So what next? So the probability that x equal to j is e to the minus lambda 1 to the j divided by j factorial. The probability that y equals to k minus j is e to the minus lambda 2 to the k minus j divided by k minus j factorial. Now, what can I factor from here? I can see that I can factor e to the lambda 2 and e to the minus lambda 2 and e to the minus lambda 1. And together, this is e to the minus lambda 1 lambda 2. Yes? And then I make the following observation. Now, we see I have here a j factorial and a k minus j factorial on the bottom. You see that? Now, what I want to see is that I look at it and it looks almost like a complete binomial theorem, you see, for K trials. You see what I'm talking about? Let me just write it again. So this is what we just calculated. Probability x plus y equal to k. We said this is the summation j equals 0 to k. Probability x equal to j. Probability y equal to k minus j. Agreed? And then when we calculated it, we saw that we can factor out an e to the minus lambda 1 plus lambda 2. And now the summation is, what remains in the summation is j equals 0 to k, lambda 1 to the j, lambda 2 to the k minus j divided by j factorial, k minus j factorial. Make sense? You see where I got the j factorial? It's because when x is equal to j, that means the probability is Poisson. It's lambda to the j divided by j factorial times e to the minus lambda 1. And correspondingly, we have this calculation here. Now you look at this and it looks very much like binomial. Do you agree? Because you see, a binomial is k choose j multiplied by j first term to the j, second term to the k minus j. So I want to place here a k factorial. So you see, so if I place here a k factorial, I can write it as e to the minus lambda 1 plus lambda 2 and divided by k factorial. That would be the same as k factorial, j factorial, k minus j factorial, lambda 1 to the j, lambda 2 to the k minus j. Yes? And what is this? This is the binomial expansion for lambda 1 plus lambda 2 to the power of k. So this is just simply e to the minus lambda 1 plus lambda 2 divided by k factorial, lambda 1 plus lambda 2 to the power of j, which verifies that they are distributed according to Poisson with the different parameter, the sum of the expected value. Good. So what next? You can see it. Next, another theorem. If x and y are Poisson, and there you have parameters lambda 1 and lambda 2, and x and y are independent, then what's the probability that x equals to k, given that x plus y is n? You see? And it ends up being a binomial distribution. It's almost not surprising, you see, because each trial we had n trials. That means we had n trials, and this is how many successes we had. And then what's the probability of those number of successes? But let's verify how that works. So probability that x equals to k, given that x plus y is equal to n, is the probability that x plus y equals to n. We already know that this is Poisson random variable with the distribution e to the minus lambda 1 plus lambda 2, lambda 1 plus lambda 2 to the n divided by n factorial. Great. This we already verified. X and y are Poisson, that's assumption. And they have each in its own parameter, and that's the probability that the sum is equal to n. So then numerator, they're independent. So if this happens, what's the probability in the numerator that we have k successes and x plus y is equal to n? That means we had k successes for x and n minus k successes for y, and that's and that when you combine, you have this. So you see that e's disappear, they cross out, and we just have this expression. Now, once you rearrange, it's the same as n factorial k factorial minus k factorial, product of those, divided by this, right? And then I can just break this number apart. I can break it into power k and power n minus k. So I just take this, and I have lambda 1 over lambda 1 plus lambda 2 to the k, and lambda 1 plus lambda 2 to the power of n minus k. I combine it. And you can see that I get a binomial distribution. So here is an example. So number of people entering post office on any given day is a Poisson random variable with parameter lambda, right? Because why would you make such a statement, guys? Why would you make such a statement? Let's pause for a moment and think, okay, what are we imagining? Or at least what do I imagine? I imagine that you have 1 million citizens, or maybe several thousand citizens in a particular district. And each of those citizens is independently going to enter this post office with some very small probability. Like many of you do not enter the post office, right? Probably by now, you never enter the post office. At least I never do, right? I'm not even sure it exists. So lambda is that average that you can calculate. So it's assuming, right? So it's like you see, you go to a post office, one day you see 5 people, another day you see 10 people, another day you see, and you average it, and that's how you figure it out, okay? But you don't exactly know how many people are in this district, but you imagine there are thousands of them, and you rarely see anything close to that number in the post office, right? You see a few, right? So that's why we are assuming it's the Poisson distribution. Show that each person who enters the post office is a male. So show that if it's a male with probability p and a female with probability 1 minus p, the number of males and females entering the office are independent Poisson random variables. Question understood? So we are assuming that we can even calculate how much it is. We're assuming that that males enter this post office with some particular probability p, and if not, then it's female, right? So what happens? So X is the number of males in the post office, and Y the number of females, and Z is the total number of people in the post office, right? So I want to understand what's the distribution of, what's the probability that X is equal to K? What's the probability that I have, that's how I decide to calculate it. What's the probability that K men enter the post office? That's the question, yes? So that is what? That is that means that total people is at least K or more, and those are disjoint events. So I take the probability of the union, and what do I get? I get the probability that X equals to K, given Z equals to N, probability that Z equals to N, and I take the summation. Yes. Now, what's the idea of the distribution? It's like a mixed distribution. Once I know how many people, each person is independently equally likely to be male or female, not equally likely, sorry, is a male with probability p and a female with probability 1 minus p. So yeah, so then what is this number? Px equal to k, given that z is n. Given that I have n people, the probability that k of them are males is n choose k, p to the k, 1 minus p to the n minus k. That's this, right? Each of them is a male with this probability that I have k males. And the probability I have so many people is e to the minus lambda to the n over n factorial. Agreed? Now, what do I get from the summation? Look at this carefully. Now, if I factor out n choose k, n factorial cancels the n factorial. I have then I have what? then I have n minus k factorial. That's over here. You see, so what I do is I break this expression apart. Let me maybe show you again on a separate slide. So what we're saying is what is probability that x equal to k given z equal to n, probability z equal to n. I try to simplify this quantity, right? It's part of the summation. So what do I get? I get n factorial divided by k factorial n minus k factorial, agreed? Times p to the power of k, 1 minus p to the power of n minus k, times e to the minus lambda, lambda to the n divided by n factorial. So far, good? Now, what can I do with this lambda? Now, the trick is I can write this lambda, as lambda to the power of k times times lambda to the power of n minus k. And then I will group this number and this number together. And I will group this with that. Make sense? And similarly, I will break apart this guy into e to the minus lambda p and e to the minus lambda 1 minus p. If you multiply those together, it ends up being simply e to the minus lambda, as you can see. Right? Like this is e to the minus lambda plus lambda p minus lambda p. So they break up together. And I also distribute those, okay? So what do we get? We have n factorial, they cross out. The lambdas and the p's combine, right? And what do I get? I get that this expression is the same as grouping over the k as e to the minus lambda p to the power of k divided by k factorial multiplied by lambda 1 minus p to the power of n minus k divided by n minus k factorial, and not forget e to the minus lambda 1 minus p. So I separate those two expressions. So this is the second expression. Yes? And here is how it comes to play. So what we have is we have the summation n equal to k, right? So you see n equal to k, and onwards, where do you see the n? You see it only in here. You see it only in the second part. So what happens is that I can factor out e to the lambda p, lambda to the p to the k over k factorial. I can factor it out, and the remaining thing is just the summation is the summation of lambda 1 minus p to the n minus k over n minus k factorial times e to the minus lambda times 1 minus p. This thing, right? So the summation is just disappears. Does it make sense? In other words, if I sum this I sum this, whatever is circled in red, if I sum from k from n equal to k and onwards, this is n minus k is 0, and minus then it would be 1, and then it would be onwards. So it will add up to 1. It's the probability will add up to 1. Are you with me? You see, we are summing it up from n equal to k and higher. So what I circled in red adds up to 1. Do you see that? Or do I need to write it separately, guys? See, there is a summation. Summation from k to infinity. That's why I sum this thing up, right? So I have this part. I have this part. This part does not involve n. And I have this part. I think I forgot to place e to the minus lambda 1 minus p. There is an error here, right? And when I sum this thing up, what do I get? I get 1. I sum up all the probabilities for y. I get 1. And so the result is that this is the probability for x, right? And similarly, I have the probability for y. And then I can see that they are independent, because probability x equal to k, y equals to j will then be the same as probability x equal to k, y equals to j, and z equals to k plus j. And conditioning on that is binomial. We already know it's binomial. This is the probability. And conditioning on that, I can break it apart. I will see the probability of x equal to k and the probability of y equal to j. Good? Hopefully, guys, right? Let's see what else we have. Any questions? Anything I should review, or you're afraid? I mean, if you ask me a question, you will never be over. No questions? Fine. Moving on. So now, in this chapter, we probably will not have much time today to go through it, but we will begin. And in this chapter, we try to understand how you can utilize expected value to give interesting estimates of probability. So those end up being very important in proving main theorems of probability. So what you have is several inequalities. So first, we begin with Markov's inequality. And Markov's inequality relates the expected value of a random variable and its probability. So we do this. If the random variable never takes values below 0, and alpha is any real number, the probability that x is bigger than or equal to alpha is less than the expected value x divided by alpha. Okay, so that gives you an upper bound of the probability. It doesn't give you anything very precise, but it gives you an upper bound. So how do we solve that? Well, we consider alpha times probability x bigger than or equal to alpha. Okay, that's what? That's alpha times the probability of all the x's that contribute a value more than alpha, right? And if all the x's contribute a value more than alpha, then if we say I multiply the alpha over here, if I replace each of those alphas by the corresponding xk, I only increase the probability. I mean, I'm only increasing this number. You agree? You see, because here, xk, if I multiply by xk and not by alpha, I only make it larger. So I get this, right? So this expression is less than this expression or equal to it for all x, right? But because the random variable is never taking values below 0, if I add the remaining terms, I only make it even bigger. You agree? So if I add all the remaining terms, so here we have this estimate, but now I also add the xk that are potentially smaller than alpha. And that's not going to cause any problem, because I'm just going to increase the summation. And what do I get? This is the sum of, that's the exact formula for expected value. So you see alpha times the probability is less than the expected value, which is the same as saying that expected value over alpha is bigger than that probability. Good. And then we can modify this and state Chebyshev's inequality. So if X is a random variable with mean mu and variance sigma squared, then for any value K bigger than 0, the probability that absolute value of X minus mu is bigger than or equal to K is less than the square, the variance divided by K squared, by this number squared. Okay, so it gives you an estimate that X is farther than, is away from mu by more than K units. Now, how can we prove that? Clearly, absolute value of X minus mu is a non-negative random variable because we take absolute value, so it's 0 or more, right? So probability that X minus mu bigger than or equal to K is the same as the probability that the square of the first number is bigger than the square of the second number. And why did I take the square? Because the expected value of this number squared is the variance. You see, so by Markov's inequality, this is just we already did it here. You see, for alpha, you see that this is the same. This is less than the expected value of X minus mu squared divided by this number. Yes, the only reason I squared is because that allows me to go to the variance. Right, so it's this number divided by K squared, which is variance over K squared. And that completes the proof. Maybe one example. Suppose that it is known that a bakery produces X number of cakes per day, where X is a random variable with mean 50. So you agree you produce either 0 cakes or 1 cake, so X is non-negative. And we know that the average is 50. So question is, what can be said about the probability that today over 75 cakes will be produced? I'm not saying I can say too much because I do not know what's the probability at all here. I do not know how the random variable behaves, but I am given the average because maybe from past, you look at the logbook, you have this logbook of how many previous days, how many cakes were baked. And you see that on average, it ends up being 50. So I know just only the expected value. What happens then? So the probability that X is bigger than 75 is the expected value divided by 75. I mean, it's less than that number at least. That's what I know for sure. Yes, and that is 50 over 75, so it's 2/3. So I know that the probability that more than 75 cakes or 75 cakes or more will be produced is less than or equal to 2/3. It could be much less. I do not know that, but I have an upper bound for the probability. It cannot exceed 2/3. Yes, and maybe one more thing, and then we are done. Then we have to, the next class, we are going to talk about weak lowest large numbers. So if the variance is known to equal 25, what can be said about the probability that today's production will be between 40 and 60? Right? Between 40 and 60, what do we have here? So we want to estimate X being between 40 and 60. Then if I subtract 50, that means X is between -10 and 10. Yes, this -10 and 10, and that means absolute value of X minus 50 is less than 10. And here I think I made a mistake. Okay, so you see absolute value of X minus 50 is less than 10, but using this inequality requires me to use bigger than, right? Bigger than. So what can I do here? I can compare this. So this probability is 1 minus probability X minus 50 has to be, yes, it's equal to this thing, and X minus 50 bigger than bigger than or equal to 10, yes? And then this probability I can estimate using Chebyshev's inequality, right? Because this probability is what? According to Chebyshev's inequality, this is this probability, just this one, not the minus one. This one is less than or equal to the variance. So we said the variance is 25, so it's 25 squared divided by 10 squared. Just 25 squared. Just the variance is not. I don't need to square it 25, but just 25. Variance is 25, not the standard deviation. Yes. So this number is less than 25 over 10 squared, and that is equal to 1/4. You see. So that means that that 1 minus this is bigger than, right? So it means that 1 minus is bigger or equal to 1 minus 1/4, which is 3/4. So I said here 1/4, but the probability that less than 60 and more than 40 will be produced, this probability is bigger than 3/4. Understand? So it's more than 75% likely that between 40 and 60 will be produced, not less than 1/4, not like what I wrote here. That's a mistake. You understand? Because you need to have the inequality pointing this way. So I just have 1 minus, and this number is at most from 1 I subtract 1/4, which means that 1 minus it is at the very least 3/4. Good. And thank you for your patience, guys. I either smell something burning or it's in my head. I hope you take a good rest.